So factors that determine the directions of travel. Okay. So the direction of travel is, it depends on the pH of the buffer solutions. So imagine how it affects. This one we discussed before. If the pH is acidic, so acidic you think of H plus. H plus is positively charged. So a positive ion will make the amino acid become positively charged as well. Okay, so of course the reason behind it is because the amino acid, right? Try to imagine, amino acid when there are weaker ions, so it has COO minus that take the H plus. Okay, so imagine that this is the structure that I draw here. If you add acid to it, acid will come here. The H plus will come here and neutralize the negative charge and making the amino acid become more positively charged. More positively charged. So if they are more positively charged, then they will go to the negative terminal. But if your pH is alkaline pH, of course, you should expect something else. Alkaline pH, alkaline is OH minus. OH minus will react with the H plus from here, and then here become NH2, and then this become no more charge, and making the whole amino acid become negatively charged due to this part. So one of the easiest way to remember is acidic, think of H plus. H plus is positively charged, then it will make the amino acids become positively charged as well. Then it will go to negative terminal. If pH is alkaline, think of OH minus. OH minus is negatively charged. It will make the amino acid become negatively charged as well. So if the amino acid become negatively charged, then it will move to the positive terminal. So pH affect the directions of travel because of the charge will change accordingly. Okay, next one. Charge on amino acid affect the direction of travel. This is true. If the charge is positive, then they will move to negative terminal. If the charge is negative, then it moves to positive terminal. Speed of movement depends on the voltage applied. The higher the voltage, the faster the amino acid move. The temperature, the higher the temperature, the faster the amino acid move. The size of the MR of the amino acid, the greater the size, of course, the slower the amino acid move. Magnitude of charge, the greater the charge, the faster the amino acid move. Should be logic this one. Okay, now larger ions with longer side chain move slower. So should be reasonable because they are heavy. More highly charged ion move faster. Like if you have amino acid of positive 2 charge compared to another positive 1 charge, so the positive 2 charge will move faster because the charges is greater, more attracted to the negative terminal. Okay, now we will have example. You can see example later. When voltage applied, ions separate out, producing a series of lines or bands on the paper or gels. Okay, so how does it look like? You can see something like this, which is here. So some amino acid moves to the left if they are positively charged. This is the band. Band or line. So you see the notes they use lines or bands. So this is the bands or the lines. This is another band or another line. This is also another band. What band is this? These are the one which is negatively charged. So that's why it moved to the positive terminal. They are separated because of their charge. So series of bands called an electro ferrogram. Electro ferrogram. So which is this piece of paper lah. This piece of paper with many bands is called Electro Ferrogram. So this Electro Ferrogram, right, is actually colorless. Colorless. Amino acid is colorless. When it reach here, and the paper is also color, it's white color, so at the end we can't see anything. And because of that, we have to make it visible by using chemicals, which is called anhydrine, or sometimes UV light. Then you can see the bands. Then you can get the amino acid separated. Okay. So we have example here. Hydrolysis and electrophoresis of a peptide. The peptide below is hydrolyzed and the mixtures is separated by electrophoresis. So let's see this. We have to recognize the presence of amide or peptide bond, which is here and here. So hydrolysis break the bond. So it break here, and here. Okay. So that is hydrolysis. Now, sketch the pattern obtained when the buffer solution used in pH 7. pH 7, that means neutral. And what happens is, when it is neutral, the COOH will remain as COO minus, the NH2 will remain as NH3 positive. That will remain at pH 7. Okay, now you see the solution. First, hydrolyze the peptide and label each amino acid. Okay, so what happened is we break down. As you can see, we break down, and this particular amino acid, the CO on the breaking point, you change it back to COOH. This is one amino acid. We call it amino acid A. So this is the structures. The second one is here, this part. This is the second amino acid. So the breaking point, you change it back to NH2 and COOH. So as you can see here, the answer, NH2, COOH. The rest you just write back. Okay. Then the third part, they use green color. So here, this is the third amino acid. So the breaking point is here, NH, you change it to NH2. NH2, and then the rest remain. So we have three amino acids at pH 7. What happened is NH2 is NH3 positive. COOH is COO minus. So as you can see, NH3 positive, COO minus, COO minus. NH3 positive, NH3 positive, COO minus. NH3 positive, COO minus. And now we have to count the net charge. The net charge here is positive. Okay, you see here, this is positive 1, this is minus 1, this is minus 1. So 1 minus 1 minus 1, the net charge is negative 1. This is negative 1. Okay, whereas the next one, positive 1, negative 1. So this becomes positive 1, the net charge. And the third one, positive 1, negative 1, so it becomes 0. Okay. The negatively charged amino acid will move to the positive terminal of the plate. So they will move to the right. So that's why the red one move to the right. The neutral one remain in the middle. The positively charged molecule of the positively charged amino acid will move to the left. Okay, so settle. Okay, let's look at the question B first. B is where they change the pH to pH 12. Okay, try to recall back the concept of pH 12. Well, pH 12 is where it is alkaline. So there is the presence of OH minus. So the OH minus is negatively charged. So basically the shortcut is if you make the amino acid have negative charge remain. So what happened to the positive charge NH3 positive is the hydrogen ions will be taken by the hydroxide, and hence the NH3 positive will form NH2 and no more positive charge but negative charge remain. So pH 12 will change the COO minus to remain as COO minus, but the NH3 positive will not present anymore, it become NH2. Okay, so let's see the next page to find out the detail. Okay, so this is the outcome straight away. You can see COO minus remain here and here, but the NH3 positive become NH2 and it become neutral already. So when you count the charge, so we have to count it like, yeah, -1 for this, and then -1 for this. So altogether, -2. So this is -2. Okay, the middle one, neutral, -1, neutral. So the overall charge, -1. Okay, this one, neutral. This is -1. So this is -1. Okay, so now they all have negative charge. So we should expect they all go to the positive terminal. So as you can see, they all go to the positive terminal. But how come red is the fastest? Because it is the greatest charge. Greatest charge move faster to the positive terminal. And these two have the same charge. But if you look at the results, the green color is faster. And basically why? Because this is lighter. Lighter. This is heavier. Heavier, then it moves slower. Okay? So slower. So same charge, then you look at the mass. Different charge, then the higher charge will move faster. So the main factor is the charge, and then followed by the mass. Okay, settle.